G'day, in this video we're going to be looking at applying our knowledge and understanding and skills of using vectors to the context of forces in dynamics. So here we're going to start looking at content points 2.1.2 and 3. We're still at the beginning of Module 2 Dynamics, focusing on the inquiry question, which looks at how forces are being produced between objects, and then also looking at the effects of those forces, in other words, the cause of motion. So our content statements require us to look at the concept of net force. I introduced that a little bit in the previous lesson, as well as equilibrium, but we're going to apply more quantitative practices to the vector analysis of forces, both in one-dimensional and some two-dimensional contexts. And in doing so, we'll look at how we can express those vectors algebraically, as well as using vector addition concepts. That will then give us the tools that we need to be able to use to begin to solve quantitative problems around forces, applying a couple of force and vector concepts that we have looked at previously. So our learning intentions are pretty clear. Apply the vector concepts from Module 1 to forces in this dynamics module. First off, I want to look at vectors in one dimension. And to begin, I want to reintroduce this idea of net force, which we could also talk about being the resultant. Effectively, the net force is the overall force once all forces are combined. Now, what you'll see here is that the net force is equal to sigma F. Now, sigma here, this Greek letter stands for the sum of. So in other words, the net force is simply the sum of all forces. Now, if we are doing a sum of forces, that essentially is implying that we are doing addition. And if we're doing addition to forces which are vectors, in conclusion, what we can say is that the net force is simply going to be a vector addition of all forces. And this is the key concept that we're going to be using for our one and two dimensional problems. So just for proof of concept, just a couple of quick examples. If I have two vectors in the east direction, one is 7 newtons and one is 6 newtons, I can add them together and the resultant here would be F net. And in this case, that would be going in the easterly direction and would be equivalent to 13 newtons of force when you combine those two forces together. Similarly to what we looked at though for displacement and velocity vectors, if I have a vector going in one direction, a vector going in the opposite direction, essentially they're going to work against each other. So let's say that the first force was 10 newtons and the second force was 7 newtons in the west direction. The resultant or net force would be going in the east direction, and that would be equal to here, 10 minus 7. And what we could say here is that we're adding 10 and negative 7 together, negative 7 because it's moving in the opposite direction, giving us a value of the net force of 3 newtons. When we start adding two dimensions, we add, again, a little bit of complexity to the problem that we have to solve. Whether we have vectors that are perpendicular to each other or not, we can use trigonometry techniques and angle rules to be able to find the magnitude of the force as well as the resultant bearing of the force. So that's, again, still going to apply all of the concepts that we've been looking at already, keeping in mind that, again, the net force is simply a sum of forces, meaning that we can just use our vector addition techniques. In the first example, I'm going to have a force in the southerly direction being added onto a force in an easterly direction. If the first force was 3 newtons and the second force was 4 newtons, what we can then do is go about our usual vector addition process using the head to tail method, so 3 and 4. The resultant will be in an approximately southeasterly direction. That is going to be F net. Here, because the adding vectors are perpendicular to each other, we have a right angled triangle, meaning that we can use Pythagoras to find the last side. It is a hypotenuse, so we can write down that F net squared is equal to 3 squared plus 4 squared. You should be able to recognize this as a 3, 4, 5 triangle, but just to make sure that we're all on the same page, let's just do the complete working and square root both sides. We have the square root of 9 plus 16. When we add them together, that is the square root of 25, which is equal to 5 newtons. To then find the bearing, we can use the SOHCAHTOA method to be able to determine our angle here. So we can find theta. So for this example, tan of theta is equal to the side 3 divided by the adjacent side 4. And theta is equal to the tan inverse of 3 over 4, which is approximately equal to 37 degrees. Now, using that information, we can find the true bearing by extending out our south line in the northerly direction, meaning that we can do 180 minus 37. And this is equal to 143 degrees, meaning that our final answer, combining both parts, F net, is 5 newtons being pushed at a bearing of 143 degrees true. Another concept that we started to look at last lesson was Newton's third law. When we were unpacking that law, we came up with this little equation here that the force of A on B is equal to the negative of the force of B on A. I did draw up those forces and show how they were equal and opposite, but I will reinforce that idea again. So as an example, if we have, say, a box, which I'll draw up, which is being pushed by a person, they are applying a force on the box. So we could write this as force person on box, so FPB. Let's say that they're pushing with 10 newtons of force. Now the box is also going to push back on the person, and it's going to be equal in magnitude but opposite in direction. And we can write up FBP, so the force of the box on the person, also being equal to 10 newtons. But as we can see with the vector, it is going in the opposite direction. As we continue to work through more complex problems using forces and vectors, the application of Newton's third law from both an algebraic and a vector perspective will become more and more useful, as well as more necessary to effectively complete problem-based questions. Next thing I want to show you is resolving a vector into x and y components. It's something that we did in module 1 as well, but we're going to go through a little bit of a recap and a refresher. Essentially, if you have your vector f, so the actual force vector at whatever angle that it is, you can use trigonometry, whether it's cos or sine, to be able to find the magnitudes of the x and y components. So let's have a look at what that looks like. So first thing I'm going to do is draw a vector. Let's just call it vector f. We can break this up into x components and y components. So if I put a line that goes directly east from the base of that vector, that essentially would be the x component of the vector fx. In other words, if I have a vector that is going in a northeasterly direction, the fx component of that vector will just show all of the force that's being pushed towards the east. We can then also put in a vector that represents Fy. In other words, the component of the force, the overall force, the net force that is in the y direction. Now, these are theoretical forces. It doesn't mean that both of those forces actually exist, but it does break our main force vector up into two separate and perpendicular components. Now, because x and y are perpendicular, it means that we are working with some right-angled trigonometry, meaning that if we know this angle here based on our bearing, we could then go and calculate for the x and y component. So the way that you would usually do that is get your bearing. So you'd have some sort of bearing from north. Let's just call that angle T, our true bearing. You could then take the difference between the true bearing and 90 in this case, and that would give you theta. From here, you can then use simple right-angled trigonometry to calculate for x and y. In the case of fx, we need to look at cos theta. So we know that cos theta is always equal to the adjacent side divided by the hypotenuse. For this example specifically, the adjacent side is fx and the hypotenuse is f. We can then solve for fx by multiplying f up. So fx is equal to f cos of theta. And then we can also use sine to similar effect in order to calculate for fy. So sine theta is opposite over hypotenuse, which effectively is fy over f, And then we can solve for Fy by multiplying that up. So we get sine theta times vector f. Just keep in mind that these are general rules though, and won't always work so effectively depending on which direction the vector goes in. And I just like to highlight that by giving you a slightly different example. In any case, the trigonometry will always work. It just doesn't necessarily mean that cos is always going to be matched to x and sine is always going to be matched to y. So I would warn against maybe memorizing formulae like this. They aren't particularly important. What is more important is that you can apply trigonometry to any situation that's put in front of you once you get your diagrams down. So in this next example, those general formula at the top won't necessarily hold, but the trigonometry will. In this case, what I'm going to do is draw up another vector, but instead of pointing to the northeast, I'm going to get it to point to the southwest. So again, I'm going to call this F. We're going to put in our X and Y components, put in our right angle, and then we're going to say that this angle here, theta, is going to be calculated based on our true bearing. So here you could do 180 minus the true bearing, and then you would end up with theta. In this case, if I use cos of theta and say that that's equal to adjacent over hypotenuse, I won't actually be using fx for this particular formula because when I substitute in my adjacent side, it's actually fy, meaning that we can use cos theta in this example to solve for fy, which means that we multiply f up, so fy is equal to f times cos of theta. And if we were to use sine, here we would be putting in fx for our opposite side, dividing it by the hypotenuse, which is f. And then again, we would have another expression for fx, which would simply be f times sine theta. But I really do want to recognize that these are effectively the opposite of what's been put up here with the general formula that you may see around the place. And so again, what I want to emphasize is if you're just using your trigonometry and you're applying your right-angled rules or even your non-right-angled rules, you're always going to be able to solve these vector problems once there is a diagram in front of you. So just be wary about memorizing those because you may end up actually making mistakes in the long run. Thank you very much, everyone. In the next video, we're going to be looking at forces motion by analyzing moving objects on inclined planes. A lot of the work that we're going to be doing is foundational for a lot of lessons that will follow this one. There will be a prac attached to this where we'll start to experiment with looking at motion on inclined planes and taking measurements. So I'll see you in the next video.